So welcome to the 2017 William Smith Conference. The Society has a number of major conferences each year, our flagship meetings, and each has an overall theme and intent, the William Smith being the flagship science event. Plate Tectonics at 50 is a long-awaited conference, and I'm sure we won't be disappointed. For me personally, the development of plate tectonic theory is the event of the last 50 years. It's what caught my imagination over 40 years ago, and it was the reason I became a geologist, and I've never, ever regretted that. As preparation for this conference, I read Naomi Oreskes' book, Plate Tectonics, which is subtitled An Insider's History of the Modern Theory of the Earth. This was published in 2001, and if you haven't read it, I commend it to you. It's very good. It has a good overview of the cutting-edge scientific work in the various institutions that combined into the dominant paradigm of plate tectonics. Interestingly, a combination of words that had not existed a few years earlier, but has since become part of normal speech, both in and outside the scientific community. The book is a chapter written by 17 of the key players of the time, and their recollections of their work and thoughts at the time. Each of the accounts is a really good read, and it comes across as being very self-effacing. The authors also give their views on the process of scientific discovery, which is fascinating. And of course, the development of plate tectonic theory was via multiple teams, not a single scientist, quite different to major scientific discoveries a century earlier. So if you're interested in some of the history of what is one of the greatest developments in earth science, it's a good place to start. And in the first session this morning, Tony Watts will tell us more and also outline what has happened since 2001. I'm very pleased to say we have 4 of these key players from that time with us here today. We have Dan McKenzie, John Dewey, Xavier Le Pichon, and Peter Molnar. Very good to see you here. As you may know, Dan has donated his extensive archive to the Geological Society of London. His archive has been catalogued and can be searched online, and the Society has also established a dedicated website for a wider public audience. So please have a look at the screens out in the library and around the place and just have a play and dig into it. It's really, really good. You'll be able to see a small part of the valuable piece of geological history, some of the original notes and such things in the Fellows' Room during the conference and out in the library. I'd like to take this opportunity to thank Dan for his generous donation to the Geological Society. Also, as we announced at the AGM, John has sponsored a new medal, the Dewey Medal. This will be awarded annually and is aimed at mid-career geologists with a focus on fieldwork. Last but not least, I would like to thank Shell for sponsoring the conference here today. And I think that's probably enough from me, so let's get on with the conference. I'd like to pass you over to Rob Butler, who's chairing the first session. Thank you.
So thank you. Some housekeeping before we crack on, which is that, can I ask everybody to make sure your phones are off? Additionally, we're joined, it's not just people in this room who are joining this conference. There's an overspill room upstairs in the council room, and there's also somewhere like 300 or 400 different sites around the world who are following this with live webcast. Therefore, when we're having discussions, it's important we use microphones, and if people, when they're asking questions or engaging in discussion from the floor, if they could introduce themselves with their name as we do that, because the screen is basically just, well, the camera's just looking at the front here, so they won't see you guys in the audience. So we can do that. But to kick things off and get the ball rolling, we have Tony Watts, who's going to provide the introduction. So Tony, please. Thank you.
Thank you, Rob, and thank you, President of the Geological Society, for that introduction. And let me just add a great welcome to Burlington House and to this meeting of plate tectonics. By walking in through that door on the right-hand side of this slide this morning, you have joined a very distinguished group of scientists, including Geeky, Lapworth, G.K. Gilbert, Thomas Huxley, and just maybe Charles Darwin. So welcome. I speak to you today, the reason I'm here is that I'm representing the quaintly named Plate Tectonics Archive Working Group of the Geological Society of London. The group has been responsible for the archiving and for the dissemination on the web of material related to plate tectonics. And the idea for this meeting actually came out of the group discussions. So what I would like to offer today is just to briefly summarize some of the developments before plate tectonics, and then to say something about and try and justify why this is the 50th year, the 1967, and then a little bit of what happened after the development of plate tectonics. And wrap up with a sort of few maybe future challenges for us as we look to the future. So if we start on this wonderful, rich history in the development of plate tectonics, and arguably we'd have to go to Borel, who probably was the first to use the word plate in his description. He was describing the way that the strong outer layer of the lithosphere, as we call it, and the underlying weak asthenosphere, these were terms that he used in his paper, responded to geological load shifts on the surface of the Earth due to volcanism and sedimentary rocks. And he spoke of the crust behaving in a plate-like manner. And shortly, more or less at the same time, we have this remarkably creative idea from Wegener that the continents had drifted. And it set up some schools of thought. We had the Fixists, who basically believed in permanence and that the ocean floor was simply founded continent. And we had the Mobilists, led of course by Wegener, who believed that the continents had moved around and that the ocean floor was essentially the top of the layer that underlay the continents. And we had these schools of thought. And a little quote here, one of the ones I like from Wegener, pitted against the Fixists. It's impossible to have the continents foundering and explaining the oceans that way. And then, of course, in 1928, in a lecture to the Geological Society of Glasgow, Arthur Holmes presented this model, which was the first to sort of consider a mechanism for continental drift. And he saw that the outer layer of Borel, the lithosphere, was being stretched and being pulled, and due to convection currents in the underlying weak layer. And perhaps here was a mechanism through the stretching and the pulling for foundering continents. And Jeffries made this little remark, perhaps a little bit in riposte to the Wegener's statement, that there was no geophysical evidence against vertical movement if the geologists, essentially if geology required it. And so we had this tussle between the mobilist, Holmes, and the Fixist community. And probably and arguably the most important proof of continental drift came from paleomagnetism, and that is the measurement of the total magnetization vector of rock samples from different continents. And it was shown very clearly by Runcorn and Creer and Collinson and others that the continents, particularly Eurasia and North America, had different polar Wanda curves. So they used the total magnetization vector in the rock samples to deduce the poles, the apparent poles, and then found that when you corrected for the 30 degrees of rotation that had gone on, for example, for North America, that suddenly the curves all lay on top of each other, meaning that the continents had drifted. And I think arguably you could say that this was the first sort of direct proof of continental drift. And interestingly, in the archive, or one of the archives in the Geological Society, is Ted Irving's archive. And you can go to this as a resource for this argument. So this was in the 1950s, and arguably the most important thing that had happened in the 1950s was the use of technologies that had been developed during World War II for military purposes. For example, sonar techniques, seismic techniques using explosives in the oceans, and sonobuoys using devices to receive signals in the oceans, and finally magnetism. And probably the person that took most advantage of this was a geologist at Princeton University, Hess, who was commanded to captain a troop ship in the Pacific during the war. And he managed, the ship was equipped with sonar, and he managed to find 160 geos. These are flat-top seamounts that were once ocean islands, had been wave-trimmed, and then subsided on the sea floor. And somehow he managed to do this in wartime, in the wartime America. And it was the sonar instrument, the development of a continuous depth recorder on a ship that was then used on research ships and used by Hazen and others, particularly Hazen and Tharp and others, to map the seafloor. And the image you see here is the first, was called a physiographic diagram of the North Atlantic. And it shows the Mid-Atlantic Ridge and running down through the Central Atlantic with a rift valley and rim mountains, very clearly demonstrated in these maps, using this technology that was developed during the war. Hess picked up on this idea of the Midocean Ridge, and he came up with a model, a remarkable model in 1960 in a lecture. The paper was not published until 1962, where mid-ocean ridges were actually upwelling, convecting mantle that took on water. And as the upwelling material pushed material out the way, it essentially created a spreading of the seafloor, lateral motion of the seafloor, so that the velocities that were recorded on the, from seismic experiments of Ewing and Rate and Revell for the thicknesses and the velocities of the crust were very low at the mid-ocean ridge and then increased. And he explained this by the cooling off and the densification of the crust with age. And he essentially understood that the age of the ocean floor increased away from a mid-ocean ridge. And you can see this by that little overstepping of sediments onto the edge of the mid-ocean ridge there in that diagram. And he had a mechanism, and it involved, again, like Holmes, it involved a convecting mantle. And who came up with the idea of seafloor spreading and the discussion of that? And Dietz perhaps has priority in terms of seafloor spreading, but Hess and Dietz together use that term. And then just 1 year later, 1963, the Vinan-Matthews hypothesis. Using the technology now, the magnetic, using towed magnetometers behind ships, to record magnetic anomalies at the mid-ocean ridge. And they showed a magnetic anomaly low over the median valley of the Carlsberg Ridge and two flanking magnetic anomaly highs. And Vinan-Matthews showed that it wasn't a case of the topography causing those and a uniform magnetization that was causing those anomalies, but they required to have lateral changes in magnetization. And he spoke about normally and reversed blocks of magnetic rocks on the seafloor and incorporated with it the ideas of Hess and Dietz on seafloor spreading. And that was in 1963. And then, as there was a flurry of activity in terms of mapping the ocean floor, Hazen and Tharp were busy, Menard and Jackie Mamericks at Scripps, and Fisher and John Matthews himself in the Indian Ocean were making more and more maps. And it became obvious that the mid-ocean ridges were a little bit more complicated in their form. They were actually offset by these narrow transform faults that you see on this 1964 map from Hazen. And this map was noted by Chuzo Wilson in 1965. And he came up with the idea that essentially of a new class of faults explaining these offsets, the motion on which was opposite to what you would predict from the offset itself. And this new class of fault, called the transform fault, required that the ridges were spreading, and that they were spreading either side of the fault, and that the sense of motion would be, in this sense, opposite to the actual offset. And Wilson actually uses the term plate in his paper to describe the regions between the mobile belts, which he spoke about in his paper, and their edges. Which brings us to 1966. So we're getting close. And what I've called here the magic profile, L-tannin 19. It was actually collected in August of 1965. And it was a traverse, a magnetic anomaly traverse of the Pacific Antarctic Ridge. The data from the ship was not reduced for 3 to 4 months, hung around a little bit. And then it was noticed by Walter Pittman. And you see here the magic profile. On the top is the actual observed profile of the magnetic anomaly. On the bottom is the bathymetry of the ocean floor with the central ridge. The second profile on there is that profile simply switched. And then the last profile is a calculated profile based on that distribution of magnetization that you see there. It's a truly remarkable. Some people have described this as the most important profile ever collected in geophysics. It was published by Pittman and Hertzler on December the 2nd. Vine and Matthews published it 14 days later in Science in 1966. The profile apparently had been seen by just a handful of people. Pittman had shown it around clearly, had shown it to Vine, and he had shown it to others at a meeting in New York in November of 1966. So just a handful of people had seen the magic profile. So then we have 67. It arrived. And quite remarkably, the first event in 67 is that AGU meeting in spring. And there were 70 abstracts on seafloor spreading. So we've gone from a handful to a frenzy of activity on seafloor spreading over that comparatively short period of time, a remarkable occurrence. One of the papers, of course, one of the famous papers at that meeting, the topic was switched. Jason Morgan was scheduled to speak about trenches, and he switched the topic. And he spoke about rises, trenches, and great faults. And it was the germs of the idea of plate tectonics were posed in this talk. And he distributed copies of the talk. The paper itself wasn't, of course, published until 1968. So a very important meeting, a frenzied meeting on seafloor spreading with this electrifying talk from Morgan that had not been planned in the original abstracts. And then a series of what I think are very important papers that bring in seismology and the arguments from seismology for plate tectonics of some sort. First of all, Lynn Sykes' crucial paper proving that that motion on the transform faults that Chusa-Wilson have hypothesized was there was actually the case in terms of the focal mechanism solutions of earthquakes. They verified that transform fault motion and therefore the lateral movements of plates against each other. Oliver and Isaacs and their study of seismic wave attenuation underneath the Tonga chromatic trench was crucial because it showed that the attenuation of the slab that was coming into the Tonga trench was the same as the attenuation in the downgoing slab, proving essentially what they called underthrusting of the plates. And then finally, this paper that we celebrate today. at the end here, November 1967. McKenzie and Parker, again involves seismology, earthquake slip vectors, and tectonics on a sphere. Here is a figure from that paper. The figure it's a Mercator projection of the North Pacific Ocean about a pole just south of Hudson Bay. And it shows, or the projection would show, horizontal meridians on this would be horizontal vectors about rotation of that pole. Apparently inspired or inspiring of this paper was the Bullard and Everett and Smith paper from 1965. And I just want to make just a brief digression here of the sad loss of Smith 7 weeks ago. And I'm sure you would agree with me in saying that undoubtedly Alan Smith would have been at this meeting if he was able. And we miss him and his contributions to plate tectonics. If we just add one thing to the McKenzie and Parker picture, which are the mid-ocean ridges, and in particular the Pacific Ridge. So these are just the present-day ridge and just oriented it about the same pole that Dan had used. And you see the elegance of this model. It was explaining not only the slip vectors at the circum-Pacific earthquakes, but it was accounting for the spreading of the ridge, essentially the subduction of the rigid Pacific plate at the trench. The elegance of this, a single plate, cannot be sort of overestimated. And it was a triggering paper, although just confined to one plate, but dealing with all of its boundaries. And it was linking different things. These authors were pulling in different observations from fields different to their own workings, and coming up with a very simple, elegant model. And it wasn't about 67. It wasn't just the two scientists, obviously. There was a great excitement, a sense of achievement here. And I just pick on one example of one institution at the institutional level. In 1967, Lamont was running 3 ships. It was doing 30 one-month cruises a year. Now imagine a university today running an operation like this. It's just unthinkable. They covered the whole globe. There are the ship tracks of one institution, 3 ships. 2 of those ships, the Vima and the Conrad, accumulated more than 1 million miles of geophysical and geological data. It was a monumental effort, and it was an institution led by a strong leadership to explore the ocean. And these wonderful quotes of scientists from a rival institution questioning the ethics, questioning the activity. So a remarkable achievement here at the institutional level. And of course, a decline set in. It's inevitable since the number of cruises decreasing from 1967. So what happened after 67? Basically lots, and you are all part of it here today. 68 was a good year. We had the extension of that plate tectonics of a single North Pacific plate to the whole globe. First with Xavier's instrumental paper in June linking the plate tectonics of all the major plates, identifying all the major plates and some of the smaller ones, and showing that they were in motion with respect to each other, and that motion was consistent with a whole Earth approach to spreading and to subduction. And then Isaac, Oliver, and Sykes in their paper saying, yes, global seismology, the evidence from earthquake seismology was completely consistent with a global framework, a global tectonics. And then an important development after a slow start. The first two legs of the Deepsea drilling project and Glomar Challenger were spent drilling salt domes in the Gulf of Mexico. But the third leg was a series of transects to drill either side of the Mid-Atlantic Ridge in the South Atlantic. And you can see the transects. And what you see here is a plot of the age of the oldest sediment in the core as a function of distance from the Midocean Ridge. It's a beautiful, spectacular demonstration that the age of the seafloor increases away from the Midocean Ridge crest. And it proved seafloor spreading. And I think we can say without any question that we had it. And this was instrumental in it. And then, of course, we'll hear more about this later, the extension of the global plate tectonic scheme came in 1970 to the geological record, and to, in particular, shown here, to mountain building. And the idea that the interactions of plates, not just today, but in the geological past, could account for so many sedimentary, volcanological, metamorphic, petrologic events in our record. And the plate tectonics did this for us. It provided this framework to explain geology, and perhaps going back as far through these collisional models, for example, perhaps going as far back as the Archean. So, what do we have? We have plate tectonics. We have it's undoubtedly a revolution of earth sciences. Some have described it as a paradigm. Maybe it was, maybe it wasn't. Maybe this meeting will finally decide this question. We have some talks on this issue. It followed speculations on continental, creative and speculative work on continental drift, and a decade of intense oceanographic exploration of the seafloor. It involved a small number of people at a relatively small number of institutions. And it came late in the history of our subject, 160 years after the founding of the Geological Society of London. It took that long. But when it did come, it was widely accepted. So what happened next? Well, there were a number of ways of answering this question. I decided to look at the William Smith lecturer of 2017 and look at what the William Smith lecturer did as for guidance of what to do. The William Smith lecturer worked on plate tectonics initially, and then he expanded. He was using all this excitement of plate tectonics to go into a wide variety of topics and subjects, which he must have seen were linked in some way that few of us here can imagine. They involved the driving mechanism of plate tectonics, mantle convection, gravity, and topography. They involved vertical motions of the lithosphere we see in sedimentary basins and in magmatic settings. And they involved studies of rigidity of the lithosphere on short and long timescales. He saw this connection between all these different things, and plate tectonics was so exciting because it generated this vision in someone in its post-activities. And we have a lot to thank him for that, because many of us cannot see all these links, but he must do. So what are the future challenges? And well, we can allude, and I only have time here to maybe tease you with a couple of challenges. In the ocean, what could we say as a challenge? Here is a map of the Smithsonian, from the Smithsonian compilation of historical global volcanoes. Now, in the early 70s, a ship, it was actually a Vima cruise, traversed, you may not be able to see the ship track, just east of Japan and the northern part of the Mariana Trench. And here is a track of the bathymetry of the seafloor. The red dots are simply to show you the regional depth of the seafloor. Sticking up from the bottom of the seafloor are these volcanoes. Dozens of them, one after another. They're like drawing pins on the floor of the ocean. If you then interrogate all the 5,500 cruises that have been acquired since this VEMA cruise and ask it to find you all the seamounts, all the potential volcanoes, you would get a map like this. So what is this? And what is the structure? What are the structures of these things? What are their isotopic composition, trace element chemistry of these rocks? What are they doing? How do they fit? What is their mechanism and placement? How do they fit into the global tectonic framework? Are big questions. These are activities within the plate itself, not at the plate boundaries. We need to know the answer to this. And still, the ocean floor is still very poorly surveyed. Less than 10% is covered with swath bathymetry, and we need clearly more information to map and chart out these features. And in the continents, an analogous problem in the interior of the continents. We have these vast cratonic basins, which are areas of vertical motions. We may have 23, 24 or so of these features. They're in the interior of the plates. They seem to be associated with very thick lithosphere, and we need to understand them. They form far from plate boundaries, and a challenge is to understand their mechanism. As you can see in this data, there's no clear evidence of extensional or compressional strain in the basement immediately below those basins. So how do they form? And how does it link in to the plate tectonic theory? So, which brings me neatly to this meeting, the William Smith Lecture and the McKenzie Archive. You've responded very well in submitting your abstracts and the titles of your talks. The word cloud shows that plate tectonics is there. So well done, everyone. We have the meeting, which I hope that many of the things, and some of the things perhaps that I mentioned will get clarified. The William Smith Lecture is the 70th in the history of the Geological Society. And we greatly look forward to that at the end of the meeting. And then we have this magnificent archive, which I do recommend you interrogate. And you will learn there are 72 boxes of the McKenzie archive. And here is a picture that Fabian allowed me to take when I was looking at 1967. And those glasses are my glasses. And I hope that you will do the same and investigate this hugely important archive. And the President has mentioned the new exhibition, which starts today, in which you will get glimpses of that archive. And it starts in the lower library, and it ends in the Lyell room, and it goes on until the end of the year. So it's going to be there. And here is the web link to the archive, where you will get glimpses of the archive. And we do recommend you do just that. So I conclude by thanking you all for coming. There are 166 of you from 6 plates. Amazing achievement. There are over 200 people out there on the web, all over the world, who are listening in to your discussions. A huge thank you to the Geological Society of London and to the staff at the Geological Society of London. And I name them here. Thank you very much for all your work. And finally, our sponsors of the meeting. A big thank you to everyone, and let the fun begin. Thank you very much.
So we've got a minute or two for questions. Obviously, there's lots of discussion time at the end of these sessions as well, if anyone would like to chip in.
Yes, my name is John Hancock from Norway, into Geoconsult. But I was wondering, when you were talking about the massive increase in cruises and observations that took place in the early 60s and up to 67, how much was that driven by money from the submarine carrying atom people in the US Navy, do you think?
Well, yes, the Office of Naval Research was a major supporter of that marine activity. It wasn't until the sort of late 70s, early 80s, where the NSF became a principal source of funding of the oceanographic expeditions. So the Office of Naval Research, but the way they funded, it didn't seem, when I was involved directly with some of this funding, and it didn't seem that they were doing it out of a strategic interest. They were just providing the funds to explore the ocean. It was an exploration phase, and they recognized that. And they weren't just interested in the sediments or in the seismic velocities of the water sediment interface. They were interested in the whole picture, crustal scale, mantle scale picture, when they funded that work. So it was a truly, I think, very open source of funding with no restriction. We would get block funds for a whole year when we would sit around a table and decide on cruises. It was a block funding of support.
Anyone else? Or we'll move straight on. We'll have, as I said, there's a general discussion period at the end of this, which hopefully will draw some of these threads together. Thank you, Jack. Next up, it's a pleasure to welcome Hank Frenkel to the podium, who's talking about. Is this your first slide?
Yes, it is my first slide. We're okay.
Morgan Mackenzie's
Right.
Discovery of Plate Tectonics.
What I want to do is briefly describe the independent discovery of plate tectonics by Jason Morgan and Dan McKenzie. It's too bad that Jason could not make it actually to the meeting, but it's wonderful Dan is here. Now, I will do this briefly. Let me start with Jason. Jason was born in 1935. He received his undergraduate degree from Georgia Tech in 1957 with a major in physics. Spent 2 years in the Navy and then embarked on a PhD program at Princeton under George Dickey in physics. He ends up finishing in 1964. Now, the important point for us is that while he was finishing his PhD thesis, which involved looking at issues in astrophysics and geophysics with regard to fluctuations in the strength of the gravity field, he decided that he did not want to continue in physics because, as he said, it was data poor. He wanted a data-rich field, and geophysics was perfect. Lots of unsolved problems, lots of data to explain. Now, as has already been pointed out, he had planned to read a paper on the origin of trenches at the 1967 AGU meeting in April, okay? He had already actually written about the origin of trenches. He did that while a postdoc, okay, working for Walter Elsasser. Harry Hess had the vision of building up Princeton's geology or geosciences by hiring geophysicists. And he first hired Walter Elsasser in 1963. So when Elsasser and Hess found out that Jason was interested in geophysics, they immediately offered him a postdoc, and he's working with Elsasser. Now, the first thing he did with Elsasser, as I began to say, was look for try and figure out the origin of trenches. Now, for our purposes, all we need to know is the account he offered required a really lack of rigidity in the upper layer of the earth above trenches. This was counter, okay, to the views of those at Lamont. Where's Xavier? I've never met you one. Okay. As Xavier was one of the people who did not, in fact, like this view because their gravimetric data indicated rigidity. Nonetheless, and Morgan had argued with him a little bit before, Jason planned to present a talk on trenches at the 67 meeting. What happened? What happened is he discovers plate tectonics. And the first thing, and how did this happen? Well, he was looking in a paper by Bill Menard. The paper was published in January of 67. Menard was lamenting the fact that no one had an adequate solution to the origin of these great fracture zones. And he wanted to show that they approach great circles, okay, the fracture zone. And what he did here is he had this great circle projection. Good. Okay, well, Jason looks at this figure. Given his training in the Navy in navigation, it wasn't time, worthless time. It was well spent. And especially a day when they looked at various map projections to see how great circles and small circles would appear in the map projections, what happened is Jason looks at this and says, well, wait a minute. These are actually concentric small circles. And then he thought of Euler. He thought of Euler. He had learned about Euler as a junior physics major at Georgia Tech. Viewing the great fracture zones as fossilized transform faults, there you go. Okay, that's the first move. He's got sort of this inchoate plate tectonics idea. He's got part of a solution to their origin. Okay, what he then decides is, I've got to look at an active spreading area. And he looks at the African block, as he called them blocks, okay, relative to the American blocks, and he treated that as a single unit, North and South America. Okay, and the first thing he does is he wants to find the Euler Poles. So he drops great circles perpendicular to the common transfer faults, and yes, we've seen this slide already, but not fixed up by Jason. Okay, this is from Thorpe and Hazen. He drops them, and he gets an intersection here, and he gets his estimate of the Euler pole. Okay? Now, what he does is he does essentially the same thing that George Bacchus did in 1964 when he proposed a way in which to test Mine and Matthews. His proposal was not funded. There was a paper. Okay, he does this while he's at Cambridge on sabbatical in 64. The point simply is as follows, that the maximum rate of spreading will be at the Eulerian equator, okay, and then it will decrease by a sine curve to the poles. So what Jason does is he calculates what the spreading rate should be, and he compares that with the available data, and he ends up with this wonderful fit. Okay? So this basically establishes the rigidity, and he views it as the initial proof for plate tectonics. Now, his initial talk, and we should thank Xavier for actually a later getting published, we historians love this, getting published the extended outline from the talk that Jason gave. And the only other thing he really does at the opening meeting, the 67th meeting, is he presents sort of the basic core ideas of plate tectonics with that figure. We've got rigid plates, we've got the three kinds of boundary, we've got rotation in accordance with Euler. Okay? Now what I'd like to do is briefly look at what he does in 1968, some of the key additions to his first publication, okay, that he didn't do at the meeting. First of all, we have this famous figure, okay, of these key blocks, key plates that make up the outer surface. And there's one thing I want you to key on, and I don't think I have to point the pointer at it because you all know, the Wanda Fook plate. Okay, we're going to see this with Dan and Parker's presentation too. What happens is Jason realizes there has to be a separate block there because the data for the movement of North America relative to the Pacific, okay, is incompatible with the data he gets here when you look at the Wanda Fook Ridge and spreading rates. He hypothesizes here a trench, okay, for the third side of that plate. The next thing he does is he realizes that besides using transform fault trends, he can use the strikes of earthquakes that occur within transform faults. So he looks at Linsight's results here for the Atlantic. Doesn't work too well, does it? Now, that wasn't a fault with plate tectonics, as Jason pointed out. It was a fault with the accuracy of Lin's data at this point. So there really wasn't good data, okay, for first motion study earthquakes in the Atlantic at this point that he was aware of. The next thing he does is, and I'll just go through these quickly, is he looks at the rotation rates of North America relative to the Pacific relative to Antarctica, and then finally closes the loop with Antarctica and Africa, okay? When it comes to his position of the Euler Poles for the movement of the Pacific relative to North America, he's able to use simply transform faults, okay? Because he's got a 42-degree separation here from the most northern transform faults and the most southern. And this is his estimate, okay? He also, in this case, tries again to use first motion studies of earthquakes in the transform faults. And here you've got that one huge outlier, but you've got, you know, a pretty good match there. Moving now to his work on the Pacific and Antarctica, okay, with those blocks, he does the same thing he originally did with regard to the Atlantic. He uses the transform method to determine the Euler Poles, which he's doing right here, and then he simply tests that using the available seafloor spreading data. Okay. Now, I want to conclude with two comments now about Jason. The first, which is not up there, is simply that he originally did not believe there was very strong rigidity, okay? Obviously he does when he develops plate tectonics. And as he eventually did, he cited Elsasser as help in that, because Elsasser had this idea of a technosphere. He was working on Hessian dynamics at that point, okay? So that also helped him a little bit. But basically, it was the proof he got once he began with plate tectonics. The second thing here is, as you've been reading, what Jason does, and Dan will do this too, what Jason does is he jettisons the Hessian dynamics of seafloor spreading from what he takes as the key part of seafloor spreading for plate tectonics. No dynamics whatsoever, okay? So he divorces this intimate tie with Hess of strong mantle uprising convection currents and the formation of a ridge, okay? That's gone. Now let me turn to Dan. I want to get Dan to this point. Okay, this is a retrospective comment he made. Now, Dan's move to finally be in this position is a little more torturous than Jason's was. Okay, Dan was born in 1942. His undergraduate career was at King's College, Cambridge. And by that time, it was clear that he wanted to be a scientist. And you have to select three sciences to work with as undergraduate, as many of you know, okay, at Cambridge. And the physics and chemistry were obvious choices. The next one was, what should the third science be? Well, he was advised physiology. Well, fortunately, he found those textbooks extremely boring. Okay, so he goes over to King's College Library. They had two books in geology, Geikie and Lyell. He reads them. He's fascinated with the breadth of what they talk about, with their interest in new ideas. He decides, I'll do geology as my third science. Unfortunately, after a year of classes at the Sedgwick, he decides no more geology. Now, to be fair, it's not that the classes were poor. He enjoyed the classes to an extent, but they were very limited in scope. And that's not what he was really interested in. So he decides on theoretical physics. Now, come Dan's his last year at King's, he's come to the conclusion, and also had found some physics lectures a little bit boring, but he's come to the conclusion that he's not going to be one of the few to make a fundamental discovery in physics. So he's looking around for what else can I do? Fortunately, he had befriended Drum Matthews. Drum was unmarried at the time and lived at King's. And Drum said to him, quite wisely, and Dan was wise enough to follow his advice. Here's what Drum said. Walk across from the Cavendish up the little gentle hill to Mattingly Rise. Talk to Teddy Bullard. Tell him you want to work with him and get a PhD in geophysics. Dan did exactly that. So we're lucky for Lyell and Geikie, aren't we? Now, he begins his PhD program, and two items I want to focus on entirely, actually. The first is, Dan really didn't care too much about continental drift then, and the controversy over continental drift, okay? He knew about Irving's apparent polar wander path and how crucial that was, okay? So he knew about the strong paleomagnetic support for continental drift, Creer, Runcorn, Irving, Clegg, Black, etc. But unlike Teddy, his supervisor, Teddy was convinced in 1963 and became a mobilist because of that. Dan, not only not that interested, but not that convinced. He knew, of course, about Fred's hypothesis and Drum's hypothesis, but in 63, 64, the data was not really very strong for them, okay? So he remains neutral. The second point, Dan became interested in mantle convection. And for his PhD thesis, he took on Munk and McDonald, who in 1960 had argued, given the ellipticity of Earth, the viscosity of the mantle had to be sufficiently great to rule out convection, okay? So what Dan did was, first he read a lot about fluid mechanics, and he read a lot about the way ceramics behave under high temperature especially, and also pressure. He ends up disagreeing with Munk and McDonald. He argues that you can still have Earth ellipticity so long as the lower mantle is sufficiently viscous, but you could have mantle convection in the upper mantle, okay? He presents this, the guts of it, I guess, at the NASA meeting in which you've already referred to, the Goddard Space Conference meeting in November of 1966. Now, this is the meeting where Fred Vine presented that incredible marshalling of evidence in support of the Vine-Matthews hypothesis. Not just Deltana 19, not just that magic profile, but the Recongenus Ridge profile, and moreover, the work that he, Wilson, and Hess had done on the Wanda Fook in 65 at Cambridge. Okay, so he presents all that. Color pictures, too. It's basically the science article in color, okay, that came out. And Dan also heard Lynn Sykes. He heard Lynn Sykes defend the idea of ridge-ridge transform faults with its first motion studies. Okay, so those two papers convinced Dan that, in fact, seafloor spreading was correct, continental drift. He became a mobilist. He returns to Cambridge to take his PhD orals at the end of 66. And he's waiting to take them, and now he's thinking about how could seafloor spreading work. He's now a believer in it. And just like Jason did, Dan, a little bit before Jason, what he does is he severs the connection between the strong upwelling convection currents and the formation of ridges. He called the ridges rootless, okay? Yes, there's still convection not involved, but not near like Hess had maintained. And this, in particular, solved the following difficulty that had faced seafloor spreading. Why is in Antarctica and most of Africa entirely surrounded by ridges? Okay, you see the problem. And in fact, Wilson knew about this problem, and Dan and Wilson talked about it at Cambridge in 65. So when Dan severs this relationship, now we don't have that difficulty facing seafloor spreading. Okay, Dan, after he takes his orals, leaves at the very end of 66 for a postdoc at Caltech. He resigns the postdoc at the effective end of June. He finishes, while there, his paper on rootless ridges, and he goes off to Scripps, where he has another postdoc. Okay, all this is recorded, there are letters to that effect and so forth. So he gets to Scripps at the very beginning of July. At that point, Bill Menard was either already gone, because he goes to sea on the 3rd, okay, of July, or he's about ready to leave. In addition, John Slater is not there either. Now, Dan and John were reunited. They were both graduate students at the same time, as was Bob Parker, okay, at Cambridge. But Slater's also at sea. He returns about July 10, July 12, something like that. Okay. So what does Dan do? Dan spends most of July reading Menard's Marine Geology of the Pacific, reading Harry Hess's papers. Okay. Oh, insert. We talked about paleomag. Hess became a mobilist and started looking for seafloor spreading as an answer after being convinced of the paleomagnetic work, especially Irving and Runcorn. Just wanted to throw that out for you, okay? All right. So he rereads, and then finally he rereads, most importantly in this case, Bullard, Everett, and Smith. And in so doing, he's thinking about Euler's fixed point theorem. He didn't learn that as an undergraduate. He learned that from none other than George Bacchus when Bacchus was working on his way of testing Vine and Matthews using Euler's point theorem, okay? The project wasn't funded, as some of you know, but anyway, the idea was perfect. Okay, so Dan thinks about the following, and this was obvious to him. It would be obvious to most of you in this room. May not have been to me, but it would have been to you. Namely, that if there are finite Euler rotations and finite velocities, then they're instantaneous ones, okay? So he comes up with that idea, or he realizes that, but he doesn't really do anything with it for a little bit. Now, exactly when, we're not sure, but it's either at the end of July or beginning of August, he realizes what's up there. For me, the critical step was realizing that I could use slip vectors to find instantaneous poles. Okay, that's the key move. So he thinks now about first motion studies and slip vectors, and it doesn't matter if they're just transform faults now. Okay, he can use dip-slip ones. And he picks the Pacific, it's gigantic, and he's got all of these dip-slip earthquakes along the trenches and the strike-slip along the transform faults. He goes to talk to Bob Parker. And when Slater gets back, okay, he's been going on to Slater about this idea. And Slater said, in retrospect, I was really interested, but I was waiting to find out if this young lady I just proposed to was going to marry me. She did, but a little bit later. Okay, so we know that Dan has come up with this idea by mid-August. Okay, we also know there was no discussion with Bill Menard at all right, at this point, at all. Okay, what do they do? This is the very first plot that Dan sent me, October 2. You'll notice he's got the Euler pole up there already. Okay, that took just a few hours when he got out that globe that he borrowed with a cap. And in this very first one, you can see the aftershocks of the '64 Alaska earthquake there, Kodiak Island region. Okay, they put that one in. Now, here's an October 11 plot. In this case, it appears that Dan is, sort of playing with the idea of maybe let's show the instantaneous rotation of North America relative to a fixed Pacific rather than the other way around. There's a hiatus of about 15 days. Dan was, I believe, at this point revising a paper, okay, that he put aside, but he had the review was there were a number of revisions. And this now looks much more like one of the papers in the actual publication, okay? We've got that kite Philippine plate down there, and we have the Wanda Fook, okay? Now, he got to the Wanda Fook with Bob Parker in a slightly different way. Concentrating on instantaneous velocities, okay? They identified a triple junction there, the Mendocino triple junction, and they figured out, given the averaging out the velocity, that there had to be a trench there. So same conclusion as Jason, slightly different way. Okay, and we've got the Wanda Fook identified here. Now, this is another plot. This plot is from November 7th. Dan asked Bob Parker to give him this particular plot, this orthogonal projection, and here you can see the slip directions or tangents to concentric circles. Now, in closing, and I got a few minutes now, okay? There are a few things I want to mention now, and I actually can tell one or two stories. One of my favorite stories that I'll go back and tell because I have time. When Dan was an initial PhD student, he wanted to learn how to write better. Now, his mother, Nan Nave Fairbrother, was a very well-known garden designer, an architect, and she'd written 3 books on it and 2 other books about raising Dan and his younger brother. She could write. So Dan obviously thought, well, that's a good idea. Let me talk to her. So she said, you know, Dan, I need a book that will tell me something about the field in which you're interested. Now, Dan had Arthur Holmes's, okay, 2nd edition. And that book weighs 5.6 pounds. It's gigantic, okay? Now, she used to like to read in bed. So what she wisely did was she took a carving knife to it and turned it into 4 volumes. And Dan wanted a new copy. Okay. Now, concluding comments. First, both Dan and Jason behaved as real gentlemen. When Dan found out from Xavier, when he met Xavier for the first time, I believe in late November, when Xavier returns to France and leaves all that huge database behind. But he had certainly gotten a lot out of it already. He learned about Jason's presentation at the AGU meeting. What he did was he talked to Bob Parker, they agreed, and Dan sent a telegram to Maddox, who was then editor of Nature. And I think Maddox, with some glee, wrote back and essentially said, basically, boys, it's just been published. That's what happens when you actually publish in a journal that publishes its papers in a timely manner. JJR should have listened to that, okay? Look what happened with Jason. Okay, and then Jason actually, when he gets Dan's paper by means of Fred Vine, he writes Jason, and there's an incredible cordial correspondence. And as you know, they end up writing a joint paper together on triple junctions. Now, I know it's not Darwin and Wallace, because in Darwin and Wallace, Darwin had done so much more than Wallace. But you remember what happened. Darwin is asked by Wallace for help in publishing a paper, and it's basically natural selection, okay? And Darwin gets the paper and goes, oh my God, okay? Lyell and Hooker helped out, and they wrote a joint paper together. That is Wallace and Darwin. The key difference, of course, is that in this case, both of them did more or less the same amount. Now, 2 more comments. First, I believe that Jason's version is obviously much more complete than Dan's, okay, of plate tectonics. But there's something about Dan's that makes it, in a way, conceptually cleaner. And that is his insistence on the difference between finite rotations and instantaneous ones. Now, this is not to say that Jason didn't understand all of that. He just didn't build it up in the same way. And he couldn't, in a sense, because he's using transform fault trends, okay, and he's using the seafloor Spradian data. And he didn't use the slip vectors. I mean, that's the huge difference between the presentations. Finally, and I guess it's appropriate because we should find out about the Nobel in physics probably today. Not just for Dan, not just for Jason, and I add Fred Vine to this, it is ridiculous that the Nobel Committee, as far as I'm concerned, does not recognize, it seems, geophysics as actually part of physics, okay? Chandrasekhar did receive a Nobel, and he did do work, for example, in geophysics, but he received it for his work in astrophysics. We celebrate the 50th anniversary. We're doing that here. AGU is going to have a session. I believe Scripps plans a session. We had several 25th anniversary sessions and a 10th. That is why? Because plate tectonics geometrized Earth science. It gave us a conceptual foundation that you didn't have before, and it still is the key foundation. Thank you very much.
Thanks very much. We have time for a quick comment. As I say, we've got a discussion afterwards. Anybody would like to chip in or join the petition for the Nobel Prize? Was there a hand in there? Oh, sorry, yeah.
Trivial, but in 68 or 69, Professor McKenzie, not a professor then, of course, did us the honour of talking to the Arthur Holmes Society at Durham, where I was a humble undergraduate, and I engaged him to talk to us. I think you have admitted the contribution that paleontology has made to plate tectonics, because Dan said to us, when I realised I had to learn 500 fossils,
Yes.
I'll ignore the adjective, I decided to do geophysics.
Thank you. You're exactly right.
Bear in mind there may be paleontologists joining us elsewhere in the world at the moment. Anyone else like to join in? Okay. Jim.
Jim Bryden, Oxford. If you've got time for light-hearted comments like that, I was at the Goddard meeting that has been referred to and will be referred to lots of times during this conference. And I went back, I was a postdoc in Oxford at the time, and I scrapped whatever seminar I was supposed to be giving and talked about the outcome of that meeting. And a lot of people in that audience naturally were really quite impressed because all the spectacular seafloor spreading evidence came out then. And at the end of the talk, Ron Oxburgh, who was in the audience, young lecturer in petrology at the time, he immediately changed his research field. I'm not sure whether it was him or Keith Cox who were not impressed by the simplicity, the elegance of the evidence that was there and the contrast with continental geology. And he said, well, that's all very well, Jim. It's all very simple and beautiful, but it'll only take the geologists a couple of years to muck it all up again. John Dewey will be talking later in the meeting.
To add that, once the work was done on the ocean floor, I mean, the ocean floor only goes back, to Jurassic? I mean, then it was continental geologists had to do something. Actually, so did geophysicists.
Thank you. Well, we can pick this up shortly. In the meantime, let's move on. And it's, if you'd like to come forward, we have Wolf Jacoby now, who's going to talk and take us further back to Alfred Wegener, and why he missed plate tectonics.
Well, thank you very much. It's an honor for me to be here because I got involved in this about 50 years ago, nearly. But I'm turning back now another 50 years to Alfred Wegener because I got involved because of the Wanda Fook Ridge. The seismic structure indicated something rising and not a Taiwanese-like route. But I also began to become very interested in Alfred Wegener with time. And so it is only relatively recent that I became aware of the fact why Wegener missed plate tectonics. He was very close, actually. He proposed continental drift on the basis of fairly good evidence. He collected a lot and reconstructed it fairly well for the last 200,000 years, but he thought it was a much shorter time. And so why did he not see plate tectonics? Why did he see only continents drift? And I think the answer is very simple. He had no oceanic lithosphere, and importantly, which I have not stressed in my abstract, also he had no asthenosphere. He had no soft, weak layer facilitating the movements. Now, first, I should remind you of the fact that Wegener anticipated seafloor spreading in the mid-Atlantic ridge. He went to Iceland on the way to Greenland, but missed some of the gaping fissures. So I thought that he may have even given up that idea to some extent, but it is the most important. I just said he had no oceanic lithosphere. He What he called lithosphere was the continental, another word for continental crust, which he thought was about 70 kilometers thick on average. And so anyway, because he had no oceanic lithosphere, even if he envisaged something like seafloor spreading, any ridge push could not be transmitted. There was no stress guide. I cannot prove this. I try now to quote a number of things which should show this. The first thing is that I remind you of the first paper he wrote in 1912. And there in one place he says, neither can I follow Taylor, who had also seen something like continental drift, who considers the mid-Atlantic ridge a relic of Homer-Land connection, something like continental crust or material below. And later on he writes, I read this to you in the English translation, since for large areas we will have to assume isostatic compensation of the seafloor, that was already mentioned. The difference means that the seafloor we believe to be old is also denser than that believed to be young. Moreover, it seems undeniable that freshly exposed zima, that's this mantle material, will for a long time maintain higher temperatures. He estimated 100 years in the upper 100 kilometers, and the later picture shows that he was actually right by the order of magnitude. The depth variation appears also to suggest that the mid-Atlantic ridge should be regarded as the zone in which the floor of the Atlantic, as it keeps spreading, is continuously tearing open and making space for fresh, relatively fluid and hot zima from depth. Now, that's a fairly good description of seafloor spreading, but as I said, since he had no rigid or no lithosphere, no plate, it was not exactly the same. In 1915, when he wrote his book, which is the famous Entstehung der Kontinente und Ozeane, he wrote sialic or sialic. Sial, that is the kind of crustal material. Sialic continental sheet and seismic seafloor, originally continuous lithosphere, he calls it there, of Earth, is totally today present only in the relics pushed together in the form of continental sheets. An argument for Sial is missing under oceans. He believes that, for instance, the simplicity of the seafloor as he knew it would suggest that there was only one material, zima, the mantle. While Sial represents a rigid plastic cover sheet, zima is a viscous fluid. That's what's important for him. Now, his picture of the Earth, this section is not, it's actually based, for instance, on earlier ideas about the Earth's interior by Wichat and others. Wegener had an oceanic lithosphere and no oceanic lithosphere and asthenosphere. Lithosphere for Wegener was something akin to thick continental crust. I mean, I've said that already. And the ocean was for him underlain by the zima, the mantle material, which was sort of continuous. And of course, at about that, I mean, in about the 20s, Gutenberg had found the low velocity layer, and things changed, and also the depth of the inner core. This is his model. This paper and picture, the last picture, were published in his first paper in 1912. Wegener clearly is distinguished between viscosity, plasticity, and rigidity. He considered Sial plastic and zima viscose, but accurate knowledge of seismicity and actually of the viscosity, as he later says, was lacking at the time. The oceanic underground was simply zima. The rise of temperature with depth correlated with a gentle decrease of viscosity. According to published data, Seal, that is a continental lithosphere at 100-kilometer depth, was stronger and harder than Zima. That was after some petrological studies and laboratory studies by Delta and also some other people. Thus, continental Seal sheets drift in viscous Zima, but a more easily flowing asthenosphere was absent. For the question whether Seal sheets float, that is again a quote, from the question whether Seal sheets floating in Zima can move, it is important that the melting points of the Sealic rocks are generally 200 or 300 degrees higher than those of semic or Zima-like rocks, such that the same temperature magmatic Zima, he calls it magmatic, and solid Seal can exist side by side at the bottom of the continental sheets. Our knowledge of melting temperatures of rocks and of temperature inside the Earth does not contradict this. Sealic rocks have no sharp melting, silicate rocks have no sharp melting points, but overlapping melting intervals, as the experiments of Delta and Day demonstrate, probably a few hundred degrees at 100 kilometers depth. After discussing temperature inside the Earth, which Wegener assumed to be gentle, increase till 3,000 to 5,000 degrees at the Earth's center, he estimated it for 100 kilometers depth to be around 1,000 to 2,000 degrees centigrade, such that the situation described above does not appear unlikely. That's what Wegener wrote. But in 1929, in his last edition of his book, he wrote, according to Ampferer, 1919, subfluence currents had carried America to the west, and Schwinner, 1925, assumes convection currents in the fluid layer due to unequal heat conduction, shifting the continental crust. In connection with this, excessive radioactive heat production in the continental sheets was considered by Kirsch, 1928. Convection currents were considered in the fluid layer. Circulating floats everywhere under continents exert an outward friction, tearing the continents apart. However, Wegener points out that we do not know anything quantitative about the viscosity of the Earth. Now, this problem of the viscosity was touched in the previous talks already several times. To me, it's a bit surprising. He knew, of course, that the viscosity was very high, closer to the surface. 100 years ago, Wegener had no stress guide to transmit ridge push and slab pull. He did not seriously consider thermal convection in the mantle. Thus, he missed oceanic plates and plate tectonics. In the end, in the fourth edition of his book, he saw that convection might be important for continental drift. I mean, he said a statement, the Newton for continental drift has not yet come. Now, of course, since Arthur Holmes, and who was, of course, mentioned, arguments for mantle convection have, we have learned a lot from theory, laboratory experiment, and so on. And today, of course, there are still many questions, but basically, I think we understand why plate tectonics exist. Essential points are continental lithosphere Seal or Sal or Seal is stronger than Zima mantle. Wegener argued on the basis of experimental data. He had no oceanic lithosphere, no asthenosphere. He had only subfluence, quoted from Ampferer and Schwinner, but no subduction. So I will not go into this. It is interesting that what people thought, how Wegener's thinking was. He was an intuitive thinker. He was trained in mathematics, but he did not use very complicated mathematics. And this is a picture from his last few days in Greenland. And I wonder whether he thought about flowing ice, flowing rock of Sima and Zia and the driving forces. But we, of course, do not know that. There's no record. So just to remind you, undoubtedly, it will first be necessary to exactly observe reality and kind of the drift before one can hope to understand the causes. Or he wrote in his, what makes it easy for me to endure the innumerable adversities of daily life is the great mission which has to be completed. So thank you very much.
Time for a quick question or two. Sure.
Just that last quote you gave is probably very important for us all. The question of reality, that Wegener didn't have the data, so he stopped where he should have stopped. Otherwise, he would have stepped out and probably made a fool of himself and gone down an avenue that he shouldn't have gone. So that's a lesson to us all, to stop with reality.
Yes, I mean, and he was quite aware of that. But I think still to say he was fairly close.
Yeah.
The idea of sticking to the data. There was a lot of time spent on trying to figure out the mechanism for continental drift, okay? And in some ways you look at it, you think it may have been a waste of time, all right? But it did do one thing in particular. By thinking about possible mechanisms, we have Holmes, Hess, and some people before, but that spawned Vine and Matthews. And Vine and Matthews and Wilson then gave a tie back to data which could be used. So the speculation's interesting, but it should be just treated that way. Thank you.
Thanks. We can return to these aspects shortly. Thank you very much.
Thank you.
And so to conclude the morning session now. I've got this right. I hope I got my time running right. We do. We have Xavier. Would you like to come forward? So it's a great pleasure to welcome Xavier Le Pichon to the stage. Would you just see in place tectonics?
Tout est dit et l'on vient trop tard. All has been said and we are coming too late. That's a little bit of my feeling today, you know. So much has been said already. So I thought what I will do first is simply to get you some insight of what I had been living through during these 2 years, 1966 and 1967. Now, at the time I was in Lamont, but I first want to give you to share with you some intimate things about myself. And this is a quote from a letter that I wrote when I was 8 years old, you know, and I was sending to my parents the vacation that I had, what the important points about the vacation. And I think you immediately realize that for me, things become real objects when they can be quantified. Otherwise, they are hard to exist. So that's a point that you have to have in your mind to understand what happened to me. The second thing, of course, and that is all well known, is this is myself, but 50 years ago, and a little bit more, 52, I think. And that we were very young people with little experience and full of hope and excitement. Okay, then the first thing, you see, with the kind of mind I have, I was always looking at tests. And the big thing in Lamont at the time, but in the science, was seafloor spreading. You were either for or against. And I was thinking all the time about how can I test seafloor spreading? You know, and I thought in 1965, when I worked on the heat flow with Marcus Langset, I immediately said, okay, that's very easy. I'm going to compute how much energy is spent in the seafloor spreading. And I will compare to the heat flow measurements of Marcus. And that's the paper we did together with Maurice Ewing, who was always adding his name to whatever paper he thought were important. So the idea, well, that's the way it worked. It was like that. You would go to Doc's place and you tell him, Doc, do you want to be on the paper? He looks at it, yes, this one, okay. So that was Lang said because he had the data. Data was the important thing at Lamont, then myself because I made the computations, and then finally Maurice Ewing because he was the boss. So the idea then was, how do you test that? And I computed that was very simple. You just brought all this hot material from the bottom of the asthenosphere, and then you compute how much heat is coming out. I compare to the heat flow. There was a factor of 3 difference, 3 times less heat flow coming out than actually the amount we measured. For a mine like mine, that was obvious. Seafloor spreading did not work. It failed by a factor of 3. And you had to have convection, like my boss, Maurice Ewing, he liked that very much, thought there was convection there below the mid-ocean ridges. And so I published that, and I went to defend my thesis in Strasbourg in April of next year, 66, in which that was my main conclusion, you know, the mid-ocean ridges, and very good thesis, very good marks, enthusiasm of all the people, but before that, I want to tell you, I think it's very important. Dan, 1 year later, made the computation the same. He used analog, a nice algebraic computation, but he obtained the same result. Actually, he tested on my model the results. So he did that, and he found the same thing than me, 3 times less heat than what he expected. Well, let's not bother. The temperature of the mantle is 550 degrees. Well, he knew, he was a good physicist, that was completely untrue. It was closer to the 1500 degree I used. But that was not important. The pattern was good. He was convinced of seafloor spreading, and right it went. You see, that explains to you the very difficult experience we had at the time. Those like at Lamont who were, you know, data was so important to collect, you had to respect data, and especially with my mind again. And those who thought that, well, and see, it's so obvious that seafloor spreading is there. Let's push that aside, and one day somebody will explain why there is this discrepancy, which is true. 5 years later, you know, we discovered that conductive heat flow is only about 1/3 of the total heat coming because of hydrothermal. Okay, next, so I come to something that I would not wish even to my best enemies, you know, to leave that. You know, just coming back from France on April 26, 1966, so proud of my thesis and so on, and finding out the magic profiles of Pittman. This we already saw. And this was such that I could not but say, yes, seafloor spreading exists. And yet I did not understand what was wrong in what I had done. You know, everything crumbled. And I had 24 hours that were horrible, you know, horrible. Again, I do not wish you to leave this such a thing, and even though you are not my best enemies. So the point is, it is very important to get back to these years, you know, to remember that all the people at the time had things like that in there. Things like, why is there tension in the trenches, you know? That was for people who were like us in Lamont, working on the trenches and seeing only normal faults. Why there? And so on and so on. So I don't want to go too much on that. But the next test that came were the rigidity test. Now, to me, it was not so much about rigidity. It was behind what I wanted to do. But the important thing I immediately realized when I received the Jason Morgan outline, that this was the way to quantify the motion, and then to test along all the boundaries. To me, that was obvious. I got the outline immediately when I came back from the AGU. Now, it's very interesting that I assisted. I saw the presentation of Jason. I was with Manik Talwani. But I was so upset by the fact that he was supposed to answer our criticism and talk about something else, and in the Morgan fashion. You know, he's the man who is best to completely confuse his audience. You know, he's remarkable for that. So the point is that the huge room, you know, full of supposedly the best scientists in the United States and probably from some other places, and none of them used this talk. None of them talked about it. And after that, he sent his outline to 10 people, and none of them used this outline. I had the outline the next day in Le Monde, so he did it immediately. And the outline, I was the only one who reacted to that and immediately started to work. And the message I got is that you can quantify so you can test. You see, to me, that was the important thing. And so I started on that, and at Le Monde, you had to work in teams. So I went to Manik Talwani, to Marcus Langseth, to Walter Pittman, and do you want to work with me on that? They no, we have no time for that. The important thing was deciphering the magnetic anomalies and get the edges of the ocean. So I worked alone. And I worked alone for 7 months, 6, 7 months. And I had to devise, my only material was this outline of Morgan. I had to devise the methods, how to make instantaneous motions, use Mercator plots. So all that I did the programs. And then I had to devise finite kinematics. You know, nobody taught me finite kinematics. I did the computer program for that, for the reconstruction. So that was a lot of work, a lot of work. And basically, this occupied me for 7 months, but completely alone. Very strange in a place like Le Monde, where they were looking at me and just laughing about what I was doing. So the thing, again, was testing, and that is found in the first sentence of my paper. It has long been recognized that if continents are being displaced on the surface of the Earth, these displacements should not in general involve large-scale distortion, except along localized belts of deformation. But there was 3 tests in this paper. And this was what I wanted to do. The first test was rigidity of each of the openings. Not so much the rigidity, but finding out the parameters that would describe the rotation. You know, and I did that for the 5 places where 5 oceans where Le Monde had enough information on that. By the second test, and I will come back to that, rigidity in the closure of plates. If it was true, you could close and you obtained the closure, and that I did. That was done by August and September. And the third test, rigidity in finite kinematics. And there I discovered all the implication of finite kinematics and the complexity that it introduced in geology that I discussed in the paper. All that, again, alone, except for one thing. I went to the September meeting, 7-8 September meeting in Woods Hole, where around Jason Morgan, he presented his paper, and there he discovered I had worked a lot, and I gave him some information. He took in this way, modify whenever he had on his pole in the South Pacific, and I used some of his information. Okay, So the basic data we had, that was the data at Lamont, that was the magnetic anomalies on the different ocean. But then after that, I tested both by obtaining the infinitesimal motions through least square processes, both for seafloor spreading and fracture zone. But then also, and that is an important point that is not mentioned anymore, at the time, expansion was still discussed, at least in Lamont. Carré had a lot of influence on the geologists. And then they found out that many people would say, well, yes, there is seafloor spreading like Hazen, but there is no subduction. And looking at that, I began to realize immediately that this was impossible. Why? Because if you stop subduction and you have only expansion, you immediately find that the equator is inflating much faster than the pole thing. And it's impossible because the Earth has to have an hydrostatic equilibrium. So I knew expansion is out. And for me, that was a big step. I was not sure because although physically it's thought stupid, if it is out, then I can make the next step, which is closing in the ocean. And I remember that was sometime in early September of '66 when I came down from work. I was working at night because the computer was available there. And I got breakfast with my wife, and I told her, look, I'm going to be the most famous man on earth. I just discovered how the earth works. I closed everything. I know how much subduction there is under Tokyo and all that. So anyway, that was, you have to realize the excitement. You don't anymore. For you, it's just standard stuff. That was incredible. And having done that alone, with only the help of this outline of Jason, to me, that had been an adventure. I was alone against the earth, and had to find her secrets. And she gave a lot. So finally, I told you, I did the first finite reconstruction of the oceans. And this is the Atlantic, roughly, in Upper Cretaceous. And I pointed out that the fracture zone would be different direction. I pointed out the average rates of spreading and so on. I did that for around Australia. And I discussed the fact that when you add finite rotation, it produces some very funny geological thing. So the whole thing, again, that was completely alone. And it was a remarkable, in my experience, it's something that has shaped me in a way. That you really have to struggle not with the other scientists. Of course you do, but that's not the main thing. But with the Earth, to find out what the Earth is doing. And then I left for France because I was offered to start a new center. And I obtained that this big logistics center in Brest would have a scientific department that I will head. And I was 30 at the time. So that was a big experience. Center which has now more than 1,000 people, but I had to hire and so on. So I left Lamont. And I knew that I was cut from the data. But that gave me a very interesting experience, which is because I could not anymore work with data. I decided I will work on the theory. And that was the origin of Plate Tectonics, the book I published with Jean Franchetot and Jean Bonin in '73. Actually, it was started because I was offered this possibility to present it at Moscow in 1972. So it started, and we had, I think, the first complete reflection on what at the time plate tectonic implied for the different plate boundaries. So that was it. Now I want to do some new stuff I've been doing and show it to you. It's just to show you that plate kinematics can still give some remarkably useful insights and change the perspective on places where thousands of geologists and geophysicists have worked, and very good one, by the way, during tens of years, and yet present something that are completely different. This I've done, it's a paper that I'm finishing, but I've worked in particular with Celal Şengör and Caner İmren from the Istanbul Technical University, and David Sandwell very nicely gave his latest gravity maps that we could work on. So I will start a little bit like Jason Morgan does sometime in his seminar. I remember the first seminar he gave in Lamont to present his plume model, and he started, the first sentence was, let us assume that there are 12 plumes coming from the core mantle boundaries in the matter. And that I thought was, well, it stunned all the people and they were not too convinced. But if you accept to go into the mind of the guy who says that, then you are forced to enter into his frame of mind and you understand better what he's trying to do. So I will tell you, look at this northern boundary of the Caribbean, plate boundary of the Caribbean, and please accept my idea that this is the best modern analog of the Eastern Mediterranean at the end of Jurassic time. In particular, the Cayman Trough, where you have more than 1,100 kilometers of seafloor spreading, which has produced this anomaly. You see the weight is with the offset in the middle, so that means it's in the middle that you have the most recent opening. The average opening was 3 centimeters per year. Now it's about 1.7 centimeters per year. And an important point is the boundaries that it produces on each side are remarkably stiff and very well structured, and I think permanent features that stay for a long time. So let's move now to the Eastern Mediterranean nowadays. Now, a very important point is that you have here, oil people have been working for quite a few years. And now there is a general consensus with the enormous amount of data that it's governed by a transform fault, which is essentially along the coast of Africa, with opening which is in this direction. These are the extensional fault, and these are strike-slip fault, and they are left lateral. In my opinion, this is the main fault which goes like that, and these are riddle faults on the side. So this extension there is the produce of big transform faulting. Now you know that at the other end, you have this Tyrrhenian slab, which represents 500 kilometers of seafloor, which is extending in this direction. You see the outline there. So the whole thing is 2,300 kilometers of a narrow basin produced by this transform fault, at least in the eastern part. Now, what's happening here? Now I look at the gravity map, the free air of Sandwell, and And what you see immediately is that the margins, the southern margin there, is remarkably linear. This is the margin over there in the same direction. And then it continues here along the outer rise of the Hellenic Trough and goes all the way to join the limit of the slab, Tyrrhenian slab. Second, always on this side of the margin, you have continental crust. This is extended continental crust, same here, west of Alfeosi Mound. And then if I fit a small circle, which I did, you obtain exactly the rotation that is predicted for the opening of the Atlantic in Upper Jurassic time, roughly between, lower Jurassic to Upper Jurassic, 175 to 147 million years, with about 800 kilometers right lateral. So to me, it's simple. That means the Eastern Mediterranean was produced at this time, and then the system that you find in it is the result of this transformation with very nice big boundary there. I cannot develop longer because I'm apparently getting out of time, but if I look at now on the topography, an immediate thing that you see is that here you have the limit of the Apulian plate, and this limit also follows a small circle. And obviously, if this is correct, this Apulia plate was about here at the limit here about 175 million years ago. And it should be a major transform. And then the only place where you could transmit the motion outward is over there, and you have to have another transform fault there. You can learn something. The difficulty, of course, now is that this whole Hellenic system has covered this part, here for the continent and there for the backstop. It goes all the way to the margin. So how do you take into account this effect and try to reconstruct this margin? This is what I have done. Unfortunately, I cannot really describe it in detail to you now. I just tell you what I did. I used two recent papers of Saxpazi et al. In 2016, and basically they describe structures that are on the slab going below the grease, and you find these fractures which are in this direction and which show vertical offset of about 8 kilometers in this area and horizontal offset, and of course the horizontal offset are such that they are compatible with the vertical offset. So you are dealing with something which happened in the slabs and has nothing to do with what happens on top. Now, through the work of people, in particular people from Cambridge, James Jackson and so on, we know the nature of this slab, in particular the very interesting thing that because it is curved around this system of the limit of the continent there, this slab is affected by compression, shortening, which is parallel to this white line, and that produces, for example, here, very strong earthquake, which is contrary to what we would expect. You would expect this direction in this direction. That means that this slab has a pattern of deformation completely different from the slab that the continent above, which is under extension. Then if you look, this is the gradient of gravity. Actually, you can see that the fractures that they describe, although they have an offset of only 2.5 kilometers there, can be seen in the gravity data. Then finally, you can think of it as the equivalent of a glacier. You know, when the ice flows, it produces grooves in the rocks below. That grooves tells you the direction it has moved. It doesn't tell you the velocity, of course, because the center of the glacier is going much faster than the edges. So here we have something which tells us the direction of motion, and it's remarkable that it goes where you have oceanic crust and not large thicknesses of sediment which are present there. And that goes along this general direction. And the problem is, on top of that, you have the equivalent of the ice, the glacier, which is the Aegean Anatolian system. And in the Aegean system here, you have the transform fault. The North Anatolian fault has not come all the way to here. So here you have no fault, and as a consequence, you have a progressive change in the velocity there. The velocity decreases compared to what it should be when you go northward, and the result is what produces the deformation of the slab below. So what we did, and that will be the end, we just assume that we reconstruct by just moving, using the rotation we have found for the slab below, moving the system of the backstop there, over there, and Greece. And then after that, we simply apply the rotation found by paleomags and by GPS and reconstruct and obtain the previous limit of this plate about 15 million years ago. You can see that here, the reconstruction, you see it goes in this general direction. The combinations of the two rotations produces this system and comes to this. And last slide, I have to end up with something from Dan McKenzie. This is in 1972 paper, and that's his reconstruction of the limit of, it's typical McKenzie thing, that is, you don't understand how with the kind of tools he had, he obtained this beautiful linear system. Again there, he knew the answer before he made the reconstruction. And it's exactly the one we obtained, which I think is the proof of his great insight. And it again comes to this problem we have in earth sciences, which is the intuition is very important, but in the end it has to be backed by some kind of demonstration which involves some kind of quantification. It was a little bit long, I'm sorry, but I was excited by this new thing I have been doing. Thank you.
Not let them run away that quickly. Yeah. Nikki.
Were you aware of, and if you were aware of it, did it have any influence on you, the paleomagnetic work that was done in the 1950s? Could you say a little bit about that?
Sure. In Lamont, the paleomagnetics was not the most important thing in the world. And but Maurice Ewing wanted to have somebody to work on that, and he brought up Dyke, who began to fight for that. And we begin to realize what that. But the thing was fairly muddy and did not really influence the people in Lamont. We were aware, of course, we were reading. Again, you have to realize the fact that we were in places where there was a culture. And the American culture was basically one of very strong fixism. And, you know, the way Maurice Ewing had made his reputation by proving that continental structure was completely different from oceanic structure, and one could not go into the other. So there were two different worlds that you had to treat separately.
Sure.
Xavier may not remember, but according to Ted Irving, Ted went to Lamont one day and talked to Neil, and Xavier and Ted went out, you had lunch with him. And as Ted said, this young gentleman told me everything I had done was wrong. So there was, sometimes we look at the data very carefully in one area, but we may not look at it that carefully in a different area. But I completely agree about your comments about Maurice Ewing.
I hope you agree with some other comments too.
Thank you. We can broaden this out to well, we already have broadened it out to involve some of the other speakers from this morning. But anyone else like to engage? I'm particularly interested in the paleomag and how that was perhaps underrepresented in the debates, and I wondered how much of that was because it was something that related to continental geology, and that was held in such ambivalence, if you like, that it was contaminated by association. But,
as an addendum, it's worth pointing out that Ted Irving failed his PhD.
Why is that worth pointing out?
Yes, Ted did fail his PhD, but even Ted said he doesn't think it was because of his belief in continental drift. It was for other reasons. The question about paleomag, I think there were several items. One was Cox and Doyle's review in 1960, and they actually do talk about Irving's apparent polar wander path for Australia, and I think that's pretty good, but you can only find that if you read the whole paper, basically, because the abstract doesn't show that at all. And in addition, they never really looked at the continuity of the APW paths. They just looked at a particular time area, here, here, here, and here. And so they missed out one, I think, of the crucial arguments. And finally, with Cox and Doyle, if you look through it, you'll see that they believe that all the data that Creer, Irving, Runcorn, Blackett, etc. used to establish continental drift was actually reliable. I mean, when you go through it that way. So I think their fence-sitting position actually had a big influence in the United States, as you said. And finally, Keith might have turned a lot of people off. Runcorn. I mean, he was a great advocate of it, but so much so, I think, that some people said, well, forget it, if Keith's that excited about it. But
I'll pass the microphone to Jim Bryden.
Yeah, there's a lot come into this, isn't there, including some relevant anecdotes. Let's start with the Cox and Dole thing. It was really remarkable that a world review of paleomagnetism that accepted or argued for the validity of the data, even in 1960, should come up essentially pretending to be on the fence, but actually slipping off it firmly on the fixist side. One anecdote. The main piece of paleomagnetic data that Alan and Dick Dole had produced at that time was from, I think, the Green River volcanics. Anyhow, Eocene volcanics within the middle of the Cordillera. And at the same time as that data was published, there were data, I think, by Ernie Deutsch on the Silit traps in India. And the poles for these synchronous rocks coincided, which I believe reinforced Alan Cox's, in particular, inclination to believe in polar wandering rather than relative motion. Of course, the explanation is that while the Silit traps data would conform to anyone's analysis of an India polar wander path now, the data from the Green River would not, because you would be talking about the block rotation within the Western Cordillera. Can I take a moment to talk about having suffered as a paleomagician for these years when land-based paleomagnetism was so even denigrated? I think I'll pick up three reasons. One is what we call the errors in the data. Just in the nature of things, typically paleomagnetic pole positions have 10-degree confidence limits around them, which means that if you're comparing two, you can easily hide a 2,000-kilometer ocean. Now, that may not disturb you if you're now talking about Rodinia or late Proterozoic geology with a culture that knows of the existence of relative motions, but in the culture that prevailed at the time, that was a very serious business. The second thing, which I admit more in retrospect than I did at the time, was the flakiness of the physics behind that paleomagnetism. There were parameters that were being used that could not be defined rigorously in physical terms. And I think the casual listener was also very easily put off by the way the data were projected, and in particular the arguments that were made for identifying the original and stable magnetization within a rock that had suffered subsequent thermal and chemical alterations. And the assertion, maybe in one of my better papers in that era, was that the real answer lay in the last 1% of the remnants that I'd been measuring and demagnetizing. And the third thing, excuse me for being so long, was defining the region for which the apparent polar wander paths apply. We've seen the polar wander path for Europe and the polar wander path for North America. What do you mean? At any one time, what do you mean by Europe? Did that include the Alps? Did it go right away across the Caledonians? The polar wander path for Australia? But most of those data came from the Tasman orogenic belt. You know, it was difficult to defend that when the word plate was not foremost in one's mind. So that really gave particularly tectonic geologists a lot of cause for skepticism. Enough.
Thank you. Yeah.
As John Hancock from Oslo again. I'd like to commend Professor Wilson for some of the work that he published. I remember way back in my early career as an oil geophysicist working on some basins in West Greenland where there was no information other than seismic. And magically, a French company, CGG, had shot one seismic line across from Canada in towards West Greenland. And there was a paper published in 1970, 71, 72 about the failed spreading ridge between Greenland and Canada, and the date from the paleomagnetics that this stopped spreading in the Cretaceous. And we could follow with this one solitary seismic line across a failed ridge, we could follow the sediments, and we could see that what was developed on the West Greenland shelf was older than the sediments that had first started depositing over the failed ridge. So very practical application, and when the wells were drilled, it was proved that there were Jurassic sediments under the Cretaceous marker that had been shown from your work. Thank you.
Any other comments or questions? We covered a whole bunch of ground there this morning, so there's plenty to discuss.
My name is David Shilston. I graduated in the early 1970s from a small university in the middle of England, and we never met any of these wonderful people who are in the room today. But what intrigued me was, in our first year, we were taught geosynclines. And I remember learning Mayo geosyncline, U geosyncline, I can't even remember them now. And then the academics must have gone away that summer, and we came back the next year to plate tectonics. And I remember learning the Dewey and Bird, was it, I've written it down, 1970 paper, learning all those diagrams, being able to draw them was a critical part in obtaining my degree. So the question I have is, we've talked about the great advances of the science. We've not talked about how the great scientists have moved it on to the great unwashed in the lesser universities, and how this new knowledge was promulgated across, and older paradigms were abandoned, presumably in the mid-70s and towards the early 80s. I'd love to hear a comment from people who were around at the time.
Sure.
Jean Archer, following the previous speaker, I was slightly earlier. I graduated in 1969. During my final year, John Dewey came and lectured to the Student Society. on the new plate tectonics and their application to the geological record. Come my final year paper that year, I wasn't perhaps the brightest, most copped-on geologist, or students, should I say, but I could not understand why so many questions on the paper came back to plate tectonics. Came back could be resolved in terms of divergent plates or convergent plates or transform faults. Now, unfortunately, I wasn't the brightest of students, and maybe my lecturers hadn't actually been at this remarkable and Pauline lecture that I went to. Maybe they hadn't listened. I'm afraid I didn't do very well in my final exams, but thanks to John Dewey, I've had a more interesting career through plate tectonics than I could otherwise have had.
Yes, Trevor Emmett. I was at another small university in the Midlands, graduating in 1976. But when I was an A-level student down in Portsmouth, there was one book that was very pivotal, I think, and it's not, I don't know if it's going to be discussed today, but a colleague of Keith Runcorn's, of course, was Don Tarling. And Don Tarling and his wife brought out a little popular penguin booklet on plate tectonics. And I think the role that played, and certainly in geologists of my generation, I think it shouldn't be underestimated.
While I'm waiting for another hand to go up, and we're going back in our old, it's a chance to live our own deep past here. But I think one of the really major things that turned a lot of people onto plate tectonics essentially before university was the rather remarkable insight by the BBC in 1972 with Nigel Calder's Restless Earth, and featuring a young Dan McKenzie amongst other people. I think it ran for 2 hours uninterrupted on BBC Two, and the idea that you could get an unbroken 2-hour science programme these days is relatively remarkable anyway, at least on outside BBC Four. But I think, but it would having colour images of volcanoes and so forth, but linked to the science behind it, I think was a real draw to many, certainly of my generation.
My question is, when Xavier's book came out, how many of you were able to read it and understand it easily? I mean, I ask that because that seemed to be a really significant book about, yes.
Well, I was just going to say how many. Well, I was just simply responding to your question, how many were able to read and understand it. So I took my first geology class. I mean, I was a physics major. My junior year, I took geology in the fall. Thought this was great. The textbook had no mention of plate tectonics in it. No. But we had some Scientific American offerings. In the spring, I took marine geophysics, and we used Xavier's book. That's where I learned plate tectonics. So just complete change from having nothing in the introductory textbook to being able to get right into that book right away.
Hi, I'm Carolyn Pascal from Birkbeck University. I lived in Cornwall. I was brought up, went to Penzance Girls' Grammar School. There was a really good geography teacher there called Mr. Dewar, and he said if you did geography A-level, he would teach you geology O-level in the first year 6, and you could do the A-level in the second year 6. And I really liked this geology stuff. There were a whole group of us, about 20. But when we came to do the A-level, he said, now, I'll tell you all about this plate tectonic stuff, but if you put it in your A-level, you must write that this has not yet been proved. It's all theory. Otherwise, he said, you won't get the marks. And I actually ended up with a B. I was a first child, so my parents decided that in Cornwall, you didn't go to university, you either went into nursing or banking. So I went to London to Secretarial College to do something useful. Otherwise, I might end up, where do you think you're going, Carolyn? An oil rig? They won't have girls on oil rigs, you're a girl. So I'm pleased to say I have just graduated from Birkbeck University, and I got a 2-1. So thank you, Mr. Dewar.
Excellent. So on that uplifting note, I suggest that we break for lunch.